Hi everyone, let's talk about surface currents. The first thing that we have to consider when we're talking about surface currents is what starts the whole thing in the first place. What's the driving force of surface currents? One of the questions that needs to be answered to get there is which way the Earth is spinning. It's the sort of thing we all assume we know, but when we think about it, we're not sure we can come up with a good answer. So even if you need to pause this video, stop for a moment and think about which way our Earth is spinning, in what direction. If you pause, thank you for coming back. So many students come up with answers such as clockwise or counterclockwise, left or right. Those are accurate answers, but they're only accurate from one perspective. For instance, if the Earth is spinning like this, it looks like it's going counterclockwise when you're looking down from the north. But if you're looking up from the south, that's not so, is it? Same thing with left or right. Left or right of what? Right? So the next thing we might get into is thinking about the sun. If we're talking about the spin of the Earth, and we understand that we're in a solar system, right? With objects spinning around the sun, orbiting around the sun, and spinning on their own axes to make day-night cycles, yes? So we all know, right, the sun rises in the east and sets to the in the west, right? That's a common knowledge concept, right? So if this is a globe, if it's oriented north, if north is up, south, to remember which way west and east is, if north is up, west and east spells we in your view. If we consider this as the sun, not to scale, of course, right? If we know that the sun, north, south, west, east, right, rises in the east and sets in the west, if you're standing right here, it rises in the east and sets in the west. But is this what's happening? Is the sun moving around the Earth? Absolutely not, right? Again, we said we're in a solar system and this thing is moving around this thing, not to scale. So in order for this to look like that's what's happening, knowing that it's staying in place, this has to be moving instead. So it's a relative motion concept. It looks like this, but it's really this is standing and we're moving another way. That said, now we know the Earth is spinning that way. The Earth is spinning towards the east. So if we know the Earth is spinning towards the east, we also know that the water in the atmosphere is not tethered to the geosphere that's spinning. So think about having a bucket of water in your hand. If you have a bucket of water in your hand, you move it forward really quickly, it's going to splash you in the face, isn't it? Because that's a relative motion response. So if the Earth is spinning to the east, water, at least at the equator, is moving to the west. And it's moving fastest at the equator because the Earth is a sphere, right? This is part of also what causes the Coriolis effect. If you have something here and something closer to the equator, so something closer to the poles and something closer to the equator, as the Earth spins, they stay next to each other, don't they? Right? But for that to happen, they have to be moving at very different speeds. This one is moving on a circumference of, a racetrack per se, about this big, whereas the one at the equator is traveling one about this big. So in order for them to stay next to each other, the object at the equator has to be moving much more quickly than the object closer to the poles. So a couple of things are happening at the equator. Number one, water is moving fastest. Water is moving west because the Earth is spinning that way, right? So Earth is going that way. All the water at the equator is moving this way, fastest anyway. And it's also warm because it's at the equator, right? The equator is the warmest part of our planet because it receives direct incidence of sunlight. Yes? So we have warm water moving west of the equator. Now water doesn't really look forward to see what's coming in its track and slows down and accommodates, right? It just goes and goes until it hits a barrier. So this water at the equator, being 0 degrees latitude, let's talk about latitude real quick while we're doing this. 0 degrees latitude at the equator, 90 degrees north at the North Pole, 90 degrees south at the South Pole. So latitude increases in value north or south from the equator. So water at the equator is moving west. It hits a barrier because of Coriolis and because it just doesn't have anywhere else to go and there's more water pushing behind it. It diverges to both the north and the south, right? And here it's hot, well, warm, and moving fast because this is where it's moving the fastest and there's water behind it. It diverges, comes around. Now once it gets closer to the poles, it has a little less pressure behind it from the initial impetus at the equator, and it's cold up here at the poles, right? So the stuff comes back down cold and slow, relatively. Right? So again, when we're in a ocean basin, and that means the bowl in between continents, right? The ocean bowl. It moves towards the west, it diverges, goes to the left fast and warm, diverges on the west side of an ocean basin, comes back around and comes back towards the equator, cold and slow, on the east side of a basin. And that happens in the northern and the southern hemisphere, sort of reflective of each other. These are called ocean gyres. The same thing happens here in the Atlantic Ocean. Now note, these things are not density driven. We have talked about other currents and our thermohaline currents that are going at ocean depth and have to do with salinity and temperature differentials. Most of these surface currents are driven by the rotation of the Earth and the winds that are also being affected by that spinning. So here we are in the west, in the Atlantic Ocean. So here we are at the equator again. The water comes through and it hits South America, right? Same thing, we've got gyre flow happening, but here, man, oh man, this is a really straight line. It just barely has to deflect all this hot water, right, for it to come right up here by Florida and the Caribbean. The driving force for hurricanes is warm water. So warm water rises, right, and it's full of water, warm air rises, it's full of water as it reaches a high elevation. It condenses into rain. When it condenses, it releases heat that causes the whole thing to happen over and over and over again. This is how they get stronger, right? So that explains the path of these hurricanes. We've always seen hurricanes coming towards Florida from this area closer to the equator, equatorial currents. That's what's happening. Now, these currents are still warm when they come here and come into the Gulf Stream, move into the Gulf Stream. The Gulf Stream is another warm current that just kind of follows up through here and goes towards the UK. So if we were just talking about latitude, you would assume, all things being equal, that it's warm at the equator and cold at the poles, right? And basically, the further from the equator you get, the colder it gets, right? But that's not the case due to surface currents. If you look at the equivalent latitude here, right, the same distance from the equator, I think everybody understands that this area is really very cold, right? This is a frozen area, very cold area. Straight across in the UK, nowhere near as cold, right? A lot of rain, but definitely a warmer climate, and that is because the Gulf Stream is bringing warmth across. So hopefully this will help you understand how surface currents affect our global climates and transfer heat everywhere.